All right, we saw in the previous section that partitions always lead to equivalence relations. So for any partition, I can define an equivalence relation. Let's now just look at equivalence relations in of themselves, not necessarily equivalence relations that come from partitions. So remember what the properties of equivalence relation are. They're reflexive, symmetric, and transitive. Okay, reflexive means that for any element in the set, it's related to itself. Symmetric means that if A is related to B and B is related to A, I'm sorry, if A is related to B, that means that B is related to A. And transitive means that if A is related to B and B is related to C, that implies that A is also related to C. Okay. Notice again that reflexive is unconditional. Every element must be related to itself. Symmetric says that if A is related to B, then B is related to A. In other words, it's conditional. It doesn't mean that all two elements are related. It just says that if two elements are related, then they're related in the reverse direction. Transitive similarly says if you have one relation followed by another relation, then you have the direct relation. And I like to think of this as saying that if you have an indirect route from A to C via B, if you have an indirect route, then you also have a direct route. There's always a direct flight. If you can get from here to here, you can get from here to here directly. All right, so again, we're going to look at equivalence relations in and of themselves without reference to partitions, and we're going to discover something quite extraordinary. Okay, so here's a binary relation. We can say that x is related to y if and only if x squared equals y squared. Okay. It turns out that this is an equivalence relation. You can go through the properties: reflexive, symmetric, and transitive. I'm going to go through these quickly because you can read this. It's pretty nice light reading. Okay. Now I can define a relation on n cross n. Okay, so n cross n is my set. The relation is going to be a collection of subsets of n cross n. So here I'm saying that two elements of n cross n are related if and only if a1 plus b2 equals a2 plus b1. So you can go through this proof to show that. Now I could rewrite this, kind of cheating, I could rewrite this as a1 minus b1 equals a2 minus b2. Next one says I have binary relation if x goes to y, if x squared minus 3x equals y squared minus 3y, and this gives me a relation which turns out to be equivalence relation. You go through all of these, you'll see that all of these are equivalence relations. All right, now there's something in common with all the examples above. They can all be defined in terms of functions. Okay. The definitions can follow this pattern. Given a function f from a to b, you can define a binary relation on A, which is the domain of f, as follows. A1 is related to A2 if and only if f of A1 equals f of A2. Okay, you can see that here. The binary relation on C, Z1 is related to Z2 if and only if the real part of Z1 equals the real part of Z2. Real part is a function. So we're saying that if the function agrees on these two complex numbers, then they're related. Okay? All right, so it seems that definitions of these form always seems to produce equivalence relations. Now we've done numerical examples. We can do some examples with different types of sets, and you find the very same thing happens. And in fact, we can prove this proposition, that if I define a binary relation in terms of a function in the following way, then I obtain an equivalence relation. If I say two elements are related if the function agrees on those two elements, then the relation I achieve from that is always an equivalence relation. Okay, so let's take stock of where we are. We've shown that any partition produces an equivalence relation, right? We can say two elements are related if they're in the same set within the partition. We've also shown that any function produces an equivalence relation. Okay, so partitions produce equivalence relation, functions produce partition equivalence relation. Is there any relationship between these two facts? Okay, in fact, there is a close relationship. So here what you're going to show is that if you have a partition, then you can create a function so that the relation derived from the partition is exactly the same as the relation derived from the function. Okay? That's summarized here. The relation derived from the partition is the same as the relation derived from the function. So just to say again, we can say that partitions produce equivalence relations. Functions produce equivalence relations. I can produce from this partition a function that gives the same equivalence relation. Okay, so you can draw that picture. It might be better actually to do it this way. Partition goes to equivalence relation. Function goes to equivalence relation. And then from the partition, I can get a function such that these two are equal. All right. So what we've said is that if you start with a partition, you can construct a function that gives the same equivalence relation. Now it turns out you can go backwards. You can start with a function and produce a partition that has the same equivalence relation. So here we give one example where that holds. You can work through this. This function, f of x equals x squared. Well, let's do these points here. Here I have the points minus 3, minus 2, minus 1. I'm going to line them up this way for a reason. So here's minus 3, minus 2, minus 1, 0. And then here's 3, 2, 1. Okay, so these are all the points in the domain. These are all the points in the domain of F. Okay. Now, I can define a relation based on this function. Here, f of x equals x squared. So if I define a relation based on this function, I say that two elements are related if the value of the function agrees. Now in this case, here I have minus 3 and 3 have the same value of the function, so these two are related. So I could draw a set here containing those two points. All right, and if I continue to do that, I will draw sets that eventually contain all of the points in the domain, which ends up being a partition. All right, so I can produce a partition from the function. Okay. And then this one generalizes that whole idea, and here you're asked to prove it as an exercise. I think that's the end of this section.